Yes, you can boil water at room temperature. Water boils at different temperatures depending on the surrounding air pressure. At sea level, water boils at 100 degrees Celsius, which is 212 Fahrenheit. But as altitude increases, the boiling point drops about 1 Fahrenheit lower for every 500 feet above sea level. This means water in places like Denver boils at about 203 Fahrenheit. Boiling occurs when water molecules gain enough energy to form bubbles of vapor inside the liquid. An experiment using a syringe shows that if you lower the pressure enough, water can boil even at room temperature without needing to be heated to 100 degrees Celsius. The text explains that boiling is not simply about heating water to a specific temperature. It depends on atmospheric pressure. Water molecules move continuously and some evaporates even at room temperature. For bubbles to form during boiling, the vapor pressure inside the bubble must equal the pressure outside. At high altitudes, where atmospheric pressure is lower, water boils at lower temperature because less heat is needed to match the external pressure. The syringe experiment demonstrates how artificially lowering pressure causes water to boil at lower temperatures, illustrating the fundamental role pressure plays in phase changes. This explanation helps me understand everyday experiences like why cooking instruction vary with location. For example, when I have been in mountainous areas, I noticed my pasta or rice took longer to cook. Now I realize it's because water boils at lower temperature so food cooks more slowly. Also, when the idea that water molecules are always moving and evaporating, even at room temperature, makes sense when I see puddles drying or water disappearing from an open glass. The syringe demonstration connects science with real life, making me appreciate how physics affect common activities like cooking. The text effectively challenges the common belief that water always boils at 100 degrees Celsius, providing a clear explanation of how pressure influences boiling. It simplifies complex scientific concepts like vapor pressure and molecular motion for general readers. However, while the syringe experiment is interesting, the practical implications, such as how altered boiling points affect cooking quality or safety, are not fully explored. Also, the text could address related applications in other fields like water prediction or industrial processes. Overall, the explanation is accurate and informative, but readers should consider that boiling is influenced by multiple factors beyond just temperature and pressure. Sometimes it's right on the box of rice mix, the high altitude version of cooking instruction. Usually, this means that your rice will have to cook a little bit longer if you are in Denver or at the top of Mount Everest. Of course, that's just a joke. No one cooks rice at the top of Everest. But why are the instructions even different? Why does it matter where you cook? The answer has to do with boiling water. You ask some people on the street about the boiling temperature of water. Some might say 212 degree Fahrenheit or even better 100 degrees Celsius. But that's not always true. As you increase your altitude above sea level, the boiling point of water decreases about 1 degree Fahrenheit for every 500 feet increase. That means your water in Denver is going to boil at 203 degrees Fahrenheit, and this will have an impact on your cooking. But why? Water vapor. There are many awesome things about water. One interesting fact is that on the surface of the earth you can find water in all three phases: solid, liquid, and gas. We call the gas phase of water water vapor. You might think that you need to boil liquid water to create water vapor, but you do not. You just need some liquid water at room temperature. Picture a glass of water. If you could zoom in with supervision, which is not actually possible, you would see that this water is made of a bunch of molecules, water molecules. Although these molecules are themselves made of three atoms, two hydrogen and one oxygen, let's just think of them as tiny balls. These tiny water balls are moving around in the water but stay fairly close to their ball neighbors. This motion isn't due to currents in the water, instead, this is thermal motion. Imagine these tiny balls jiggling around in a giant collection of balls. The hotter the water, the greater the motion of these water balls. But wait, the speed of the water particles are not all the same. Although there is an average ball speed, some are going faster and some are going slower. It's just like the height of a group of adult humans. There is an average height, but everyone is not the same. Some people are very tall, but that's just a small fraction of a total group. If you have a glass of water sitting out on a table, the water balls don't just stay as a liquid. Some of these balls have enough thermal energy to break away and become free. Free from the liquid stage means the water ball is now a gas, water vapor. Boiling is not needed to get this water vapor. But wait, it works the other way too. Some of the water balls in the gas stage can interact with the liquid water and join the liquid water balls. Water in a closed container will eventually reach an equilibrium state between water vapor and liquid water. At this equilibrium state, the rate that water molecules are freed from the liquid state is the same as the rate of water molecules entering the liquid state. The pressure of this water gas in equilibrium is called the vapor pressure. You can see evidence of this water vapor in a closed container by looking at the water that condenses on the walls. Here is what water looks like when you get it to 100 degrees Celsius in slow motion. Yes, I know you have seen this before, but it's still cool. What are the bubbles in the boiling water made of? Are the bubbles made of air? What about some hydrogen and some oxygen? No, the bubbles are water vapor. They are small pockets of water in the gas phase. I mean, they could not be air. Where would this air come from? The only option is that the bubbles are made up of water vapor. So, what is happening to make these boiling bubbles of water vapor? It's all about temperature and vapor pressure. As the temperature of the water increases, the average speed of the water particles also increases. At some point, water molecules have enough energy to push back other water molecules in the liquid phase to form a bubble. But you have to have the water hot enough so that the particles are moving in fast enough. But wait, it is also about the vapor pressure. In order to keep the bubble from collapsing, the pressure inside the bubble must be equal to the pressure outside the bubble. Inside the bubble is the vapor pressure and outside is the water pressure. This means that the water to boil the temperature must increase until the vapor pressure is equal to the outside pressure and a bubble can form. What about that external pressure? That depends on two things. First, the water itself. In order for the water not to collapse, the deeper water must have a higher pressure. So, the water pressure depends on the depth, the density of water, and the gravitational field. For a typical glass of water, the pressure at 2 centimeters below the surface is only a 0.2% increase over the atmospheric pressure, and that is the second thing that contributes to the total pressure, the atmosphere. Lower pressure. What if I decrease the atmospheric pressure pushing on some liquid water? This would reduce the pressure in the liquid as well. If I reduce this pressure enough, I can bring it down to the same level as the vapor pressure. Boom! Now the water particles have enough energy to form their tiny little boiling bubbles without the need to increase the temperature. I can even get water to boil at room temperature. Yes, you need a vacuum pump and a strong container to get this work, but you can do it. Notice that I hold onto the boiling water flex just to prove that it's not hot. Trust me. Oh, wait, you don't have to trust me. You can do it on your own. You just need one of these large plastic syringes. Get the syringe and put some water in it with very little air. Now seal up the end and heat up the water just a little bit. Here you can see my version. I used hot glue on a rubber stopper along with a Lego piece to seal the hole. The syringe was then heated to about 42 degrees Celsius, a little over 100 degrees Fahrenheit. Now I can pull the plunger out to decrease the pressure in the liquid and induce boiling. It is pretty tough to pull the plunger back to decrease the pressure, but you can do it. Oh, why heat the water up? Well, I cannot get the perfect vacuum by pulling the plunger. So, I need a little boiling help by starting the water at a higher temperature. This is exactly what's going on when you cook your rice at high altitude. Well, not exactly the same. There is not a human pulling back on a giant plunger that holds the air on Earth. The Earth's gravitational field does that for you.